So it's pretty fascinating when you think about it, right? How do scientists actually figure out how much carbon a forest is pulling from the air? And maybe even more importantly, how fast is it happening?
Exactly. The rate is often the critical piece of information.
Well, today we're doing a deep dive based on some sources looking into forest differentiation and carbon sequestration.
Hmm.
And our goal, really drawn from this material, is to connect the dots. We want to understand the link between, forest resource technology.
Which is basically using science and tech to manage forests.
Right, that technology and the rainforests capture carbon, and how that ties into college-level math you might be dealing with, specifically differentiation and integration.
It's a really direct link, actually.
Yeah, and here's where it gets interesting, especially if, like, calculus is on your mind right now. These sources really highlight this parallel. Differentiation at its core is about understanding the rate of change, isn't it?
It is how quickly something is changing at any given moment.
And that connects straight to the rate of carbon sequestration. It's literally the speed, the pace that trees are absorbing carbon over time.
And what's really key here is how practical this is. It's not just theory. In forest resource tech, knowing this rate is absolutely vital. It's not quite enough just to know that a forest sequesters carbon.
You need to know how fast.
Precisely. How fast? Sources talk about scientists building mathematical models, functions to describe the complex growth patterns.
Okay.
So imagine you have a function, let's say CT, that represents the cumulative carbon stored by maybe a tree or a whole section of forest over time t.
Right.
Well, finding C prime of t, the derivative, that gives you the instantaneous rate, the speed of carbon uptake right at that moment.
Ah, so they're actually differentiating these models that track, like biomass or the total carbon stored over time to get that speed.
That's exactly it. And this rate, it tells forest managers so much useful stuff, like which tree species are pulling in carbon the fastest.
Or are certain management things, maybe like thinning of the forest, helping or hurting that rate?
Exactly. This is speeding things up, slowing them down. It helps predict what might happen next, how healthy the forest is in terms of, well, its climate job.
Yeah.
Finding the point where that rate, CT, is at its maximum, for example, that could really inform how you manage the forest for the best carbon benefit.
Okay, so differentiation gives you the speed, the rate at any specific point.
Yeah.
But what about, the bigger picture,
Yeah.
the total amount?
Right, good point. And that naturally leads us to the other side of calculus. While these sources really emphasize the rate using differentiation, its inverse operation, integration, is just as important in the bigger scheme.
How so?
Well, if you take that rate function, CTT, the speed, and you integrate it over a specific time period, say from year 1 to year 10, or time t to t,
Uh-huh.
that calculation gives you the total amount of carbon sequestered during that whole period. It sums up all the little instantaneous rates.
Got it. And why is knowing the total amount useful in practice?
Oh, it's incredibly important. Think about carbon markets. You need a total number to calculate carbon credits, right?
Okay, yeah.
Or for countries reporting their climate efforts, they need national carbon inventories. That requires knowing the total sequestration over years. Integration lets you get that cumulative figure that policymakers and markets really depend on.
So putting it all together, what does this mean for you, maybe listening and, working through differentiation and integration problems?
Well, it really shows that these concepts you're studying aren't just abstract math exercises locked in a textbook.
Definitely not. They're actual tools. Powerful ones used by scientists, technologists out in the real world.
Yeah, they're using them to measure, to understand, and even to manage really critical environmental processes like this, like carbon capture, processes that are vital for, well, the planet.
So to wrap this up then, the core takeaway from the sources is pretty clear. The rate of carbon sequestration in forests. It's a real, tangible thing happening out there, and differentiation is fundamental to understanding how quickly it's working.
It is. And maybe a final thought, something for you to chew on after this deep dive. Think about other natural processes. Where else is understanding the rate absolutely critical?
Like what?
Maybe the speed of glacier melt,
Hmm.
or how fast a river is eroding its bank, or even the rate a population is changing, maybe an endangered species.
Right. Understanding the speed is key to managing or predicting.
Exactly. And calculus, especially differentiation for the rate and integration for the total effect, gives us the mathematical framework, the lens to actually analyze all these dynamic systems.
That's it for this deep dive.